In this video, we're going to think about the proton transfer reaction and how it applies to organic chemistry. Our goals are to be able to write proton transfer reactions for Bronsted-Lowry acid-base combinations, to predict what side of a proton transfer reaction will be favored for a given acid-base pair at equilibrium. And then finally, we would like to calculate the equilibrium constant for a proton transfer reaction using pKa data. And there's some pKa data for common functional groups that we're going to need to memorize. So as we start, I just want to take a quick time out. We need to revisit this idea of chemistry being all about electrons. Now, I understand we just talked for 30 seconds about how we're discussing proton transfer reactions, and you probably think about a proton, a hydrogen ion, when you hear those key words. And that's true, but even this is all about electrons. So go ahead and pause and see if you can just list the lowest energy places for an electron to go. And then you'll see by the end of this module how this is related to electrons. All right, pause and try. So here's what I came up with. These are common answers given to me by students. The 1s orbital is certainly the lowest energy place for any electron. The lower shell numbers are lower energy orbitals. Closer to the nucleus, or having a higher probability of existing close to the nucleus, these are lower energy places for electrons. S is lower than P. More S character, sp versus sp2 versus sp3 hybrid orbitals, sp is the lowest energy. And then finally, sigma bonds are lower energy than pi bonds because for sigma bonds, you have electron density along the internuclear axis. So that's all review, hopefully. More electronegative atoms have lower energy atomic orbitals. And then finally, I often hear molecular orbitals, at least the bonding ones, they are lower energy than atomic orbitals. So perhaps there's something else that you came up with, and you can check it with me if you have any questions. So let's review Arrhenius acids and bases. As you know from Chem 1B, there are 3 definitions of acidity and basicity, and typically Arrhenius is the one that we begin with and the one that is most useful in Gen Chem. Now in organic chemistry, this will not be the most useful definition, but we'll start here anyways. So an acid generates hydrogen ion in water. Hydrogen ion is H+. In water, aqueous solution. And we know that a solvated hydrogen ion, one that's solvated by water, is interchangeable with hydronium ion. Now, bases, they generate hydroxide ions in solution. Hydroxide ions have the formula OH-, and they're in water, so that's aqueous hydroxide. We could draw the Lewis structure. There we go. We have electron-rich oxygen here. It has 3 lone pairs and 1 bond, which is more lone pairs than usual. Okay, now, do you think that Arrhenius acid and base definitions will be the most useful for us? No. So we certainly still care about this definition, but it's not the most useful. Why do you think that is? Correct. Most organic compounds do not dissolve in water. So we won't be thinking as much about Arrhenius acidity and basicity. We will, however, be thinking about Bronsted-Lowry acidity and basicity. So Bronsted-Lowry acids donate protons, H+ ions, and Bronsted-Lowry bases accept protons. So let's look at an example of a Bronsted-Lowry acid and base. An example of a Bronsted-Lowry acid might be the ammonium ion. An example of a Bronsted-Lowry base might be the hydroxide ion. Excellent. So Bronsted-Lowry acid, it is going to donate a proton. Bronsted-Lowry base, it is going to accept a proton. So we can write what's called a proton transfer reaction between these two species. We can show how one donates the proton and the other accepts it. So if ammonium donates a proton, we subtract an H. Now we have NH3. And we subtract a positive charge. It goes from +1 to 0 as the charge and makes ammonia. So ammonia here is called the conjugate base of ammonium. Why? Well, if it accepted a proton, what bases do? It would regenerate ammonium. Excellent. So that is our first conjugate acid-base pair. If hydroxide acts as a base and it accepts a proton, then we're going to add an H to its formula. Now we have H2, and we are going to add a positive charge. So now it's neutral. So I wrote HOH, but you could write H2O, whichever way you want. So this is water. And then water here would be referred to as the conjugate acid of hydroxide. It's the conjugate acid of hydroxide because if it donates a proton, what acids do, conjugate acid, it makes hydroxide. So we have our two conjugate acid-base pairs in this proton transfer reaction. So the acid, ammonium, which you called HA in general chemistry, it donates a proton to make A-. Conjugate base, it accepts that proton. It accepts it. Conjugate base B to make HB. So in this case, it's B-, and so it makes HB. Now, every Bronsted-Lowry acid, as you know, has a conjugate base, right? Whatever it becomes when it donates that proton is the conjugate base. So let's take a moment. I'm going to write some Bronsted acids for you. You are going to pause and you are going to write the Bronsted or the conjugate base of this Bronsted acid. And I'm indicating for you the acidic proton when there's some choice. All right, so here are 3, 4, 5 Bronsted acids. So you go ahead, you think about what happens when this donates a proton and write the conjugate bases for all 5. Be sure that you've tried on your own. Okay, so here's what I have. So here are the conjugate bases for each of these acids. I've also, for fun, written the names. Now, what I'm going to do for you, for us, is go through and I'm going to draw the curved arrows for these proton transfer reactions. So first thing, I need to draw out the bonds. And I'm going to show the electrons in the bond, they go to chloride, right? So they're going to chloride. If we want to show the Bronsted-Lowry base, it's going to accept the proton, and then the electrons in that bond go to chlorine, and that makes chloride. So here's the electron pair that was in that bond. Of course, there's 3 other electron pairs on chloride. So you see at the top, I say preview, where when HA donates a proton, the electrons in the HA bond stay behind. They stay with the conjugate base, right? I want you to keep that in mind, and it's related to what we talked about at the very beginning, electrons going to the lowest energy place. All right, back to these curved arrows. So for HBr, we would have a base, can have a negative charge or not. Let's give them negative charges. It uses the lone pair to accept the proton. The electrons go to bromide. There's those electrons, and it has 3 more lone pairs. Sulfuric acid, the base accepts the proton, and then the electrons in that bond go to oxygen, and you make hydrogen sulfate. For acetic acid, some base accepts the proton. The electrons in the bond go to oxygen, and you make acetate. For hydronium, again, some base accepts the proton, and the electrons, it doesn't matter which proton you show, they're all the same, but I did show this one going away, so let's show that. There was already a lone pair on water, and then there is the new one. Okay. So really pause and make sure you've got this. When you're ready, we're going to move on. So I've already kind of given away the proton transfer reaction thing I showed you on the previous slide. So here I showed you an example of a proton transfer reaction between ammonium and hydroxide when we were introducing Bronsted-Lowry acids and bases. But let's just back it up a little bit and look at a general proton transfer reaction between a Bronsted-Lowry acid and a base. We're going to have the base accept the protons. Let's draw the curved arrow. The base accepts the proton, and then the electrons in the HA bond, they stay with A. And so we're going to have A minus, the conjugate base of our acid, and we'll have HB, which is the conjugate acid of our base that we started with. Okay, so that's a generic proton transfer reaction. You should go and look at this list that we've generated on the previous slide. So right here, take a look at this list, pick some of these acids and bases, and see if you can write some proton transfer reactions. If you had trouble choosing acids and bases, I've chosen 2 for you. So why don't you go ahead and try these. Try to write the proton transfer reaction between these 2 species. Please pause. All right, now I've done it for you here. So sulfuric acid is certainly the acid. It's going to be donating a proton. Water is certainly going to act as a base and accept the proton in this case. Now, when sulfuric acid donates the proton, it will make its conjugate base. When water accepts the proton, it will make its conjugate acid. Let's draw the curved arrows. Bases must have lone pairs. So here's the lone pair of water. It accepts the proton of sulfuric acid to make the conjugate base of sulfuric acid and hydronium. Now, I know I've been writing out sulfuric acid in this weird way, but that's because I need to show the bond, the OH bond, and so that's how I've been doing it. Now, as you know, all proton transfer reactions are at least in principle reversible. This means that HA and B minus can react to form A minus and HB, or A minus and HB can react in the reverse direction to form HA and B minus. Now, typically, one direction does predominate over the other, meaning you typically see more of one species than the other. So if the forward reaction predominates, for example, then that means at equilibrium, you will mostly observe these species. If the reverse reaction predominates, at equilibrium, you will mostly see these species, HA and B minus. All right, let's consider the reaction between the ammonium ion and hydroxide. Do you have a sense of whether or not this reaction will mostly proceed towards the right in the forward direction, or towards the left in the reverse direction? Do you have a guess? Well, I can tell you what students usually pick. Usually students say this is going to mainly proceed in the forward direction. And when I ask them why, students usually tell me, well, that's because these species are uncharged. And that is a really solid prediction. We don't need to always predict because there is some data that we can use, this prediction based on our chemical intuition, it's certainly fine. Now, we're going to get to data that we can use to help us make these predictions. So because so much chemistry takes place in water, we typically use water as a standard reference for the strength of acids and bases. Now, for any Bronsted acid HA, if you put it in water, water can act as a base and accept some of the proton from that acid, and that makes A- and hydronium ion. Now, this reaction will reach some equilibrium, and we know that the equilibrium constant for any reaction is the concentration of the products over the concentration of the reactants. In this case, the products are A-, the conjugate base of HA, and hydronium, the conjugate acid of water. The reactants are HA and water. Now, we can define the Ka for any acid, where we set the concentration of water equal to 1, as it doesn't change very much during the proton transfer reaction. And the Ka for some acid is simply the concentration of the conjugate base times the concentration of hydronium over the concentration of the undissociated acid at equilibrium. All right, so we can think about what it means if we have a large Ka or a small Ka for a given acid HA. So when I say large Ka, I mean greater than 1. When I say small Ka, I mean less than 1. So for a large Ka, a Ka that is greater than 1, that means that the numerator here is bigger than the denominator. So the major species at equilibrium is the products. So the dissociated acid and hydronium. So what we say here is we say HA is a strong acid. Strong acids completely dissociate in water to form their conjugate base and hydronium ion. So that is the definition of a strong acid. Now, if the Ka is small, if it's less than 1, that means that the denominator, the undissociated acid, it is larger than the numerator of the Ka expression. So in that case, the major species at equilibrium is the undissociated acid, HA. So in that case, that means that HA, it only dissociates just a tiny bit to donate a hydrogen ion and make its conjugate base. So we call HA a weak acid. Strong acids have a large Ka, greater than 1, because for a strong acid, it completely dissociates or dissociates a lot, and the numerator is bigger than the denominator. For a weak acid, Ka is small. It's less than 1 because the weak acid dissociates only a little bit. The denominator is bigger than the numerator. We mostly have the undissociated acid with just a teeny tiny amount of the dissociated acid and hydrogen ion. So let's think about some representative strong acids and weak acids. So again, a strong acid has a Ka that is greater than 1, meaning that it completely dissociates in solution, and A- is your major species at equilibrium. Hydrochloric acid is a good example of a strong acid and has a Ka on the order of 10⁷, so much greater than 1. What we see for weak acids is that the Ka's are less than 1, meaning that the undissociated acid is the major species at equilibrium. So for example, HCN is a weak acid, and its Ka is on the order of 10 to the negative 9. So there is very, very little dissociated acid at equilibrium. Now, there are about 16 orders of magnitude, 16 powers of 10 between those Ka's, and that is a huge, huge scale. So when we have constants like this that span this many powers of 10, we often use a log scale to think about them. So we often think about the pKa's of an acid, and in fact, in this class, we're going to focus primarily on pKa's. So like in all chemistry, the p, little p, means the negative 1 times the log of whatever comes next. So the pKa of an acid is negative 1 times the log of its Ka value. And then, of course, if you know the pKa and you want the Ka, then the Ka is 1 times 10 to the negative pKa. Let's continue thinking about the relationship between Ka and pKa for strong acids and weak acids. So we know a strong acid is going to have a large greater than 1 Ka, right? So we can look at our example of HCl. It was on the order of 10 to the negative 7. Now, its pKa is going to be negative or small. Right? So we have a large Ka, we have a small pKa. So for example, if we take HCl and we do negative 1 times 10 to the log of 10 to the 7, that's going to give us a pKa of negative 7. So if you take this Ka and you plug it in here to this equation, you're going to get a negative 7. So a small or negative pKa for a strong acid. Now, weak acids, they have small Ka's, right? They have small Ka's, meaning that they are less than 1. So if we took the Ka of HCN now, our representative weak acid, and we plugged it into this equation, we're going to get a pKa that is positive or large. So for example, for HCN, the pKa would be 9. Go ahead and verify that if you would like with your calculators. So let's try to finish these sentences. A strong acid will have a, what type of pKa? Small or negative pKa. A strong base will have a conjugate acid with what type of pKa? Think about that. So a strong base will have a conjugate acid with what type of pKa? So this is a strong base. Then that means that it's going to accept a lot of hydrogen ions, right? That means that this equilibrium constant here is going to be greater than 1. This side is favored at equilibrium. If this side is favored at equilibrium, so the conjugate acid is favored at equilibrium, that means this conjugate acid doesn't donate a lot of protons, right? The reverse reaction doesn't happen a lot. So that means this conjugate acid, if it's favored, it must be a weak acid. And weak acids have what types of pKa's? They have large pKa's or positive. This idea is really, really, really important. This idea that a strong base has a conjugate acid that is weak. It's a weak acid. Strong base, weak conjugate acid. This is a really important idea for us in organic chemistry. So I want you to take a moment and make sure you can wrap your head around all of this. When you're ready, we can take a look at the pKa values for common acids. So this comes out of your book. If you take a look, you can see that they are oriented such that you have the strongest acids at the top of the chart. You see these negative pKa values. And then you have the weakest acids down at the bottom of the chart. Whoa, large positive pKa here. Now, notice that the strongest acid has the weakest conjugate base. The weakest acid, this will have the strongest conjugate base. And this comes out of this relationship here. A strong base, by definition, has a weak conjugate acid because a strong base accepts lots of protons, and this side, the side with the acid, will be favored at equilibrium. pKa data exists for many compounds. You can look up the pKa data like this for all kinds of compounds. It's been measured by physical organic chemists. However, every chemist should really have some basic pKa values memorized so that they can make quick comparisons and make quick predictions. So these are going to be the functional groups for which you should have some quick pKa data memorized. I would like for you to pause and just list the name of the functional group and the conjugate base. And then when you come back, I'll let you know what the pKa values are for all of these common functional groups. So I filled it in for you, and we're going to navigate through this a little bit together. But I will underscore one more time that you do need to memorize the pKa values for these functional groups. Now there's going to be variation around each group, but these are good starting places. And I have, approximate numbers. So you might see something a little bit different in your textbook, but these are just approximate numbers or a place for us to start our discussion. So let's take a look. We have the weakest acids oriented at the top of this page. So we have our weakest acids up here. We have our strongest acids down at the bottom. And if we think about the conjugate bases, we'll have our strongest conjugate bases at the top because the strongest conjugate base will correspond to the weakest acid. Okay, and then we're going to have our weakest conjugate bases down in the bottom. So weakest acid to strongest acid, and then weakest base to strongest base. You should be able to draw the curved arrow mechanisms for the formation of all of these conjugate bases from the acids. So I'll give you an example with the alkane here. So here's the alkane. We would imagine some strong base deprotonating, and that would give us the conjugate base shown. Now there's a few more functional groups that we can add to this chart that are pretty useful to know. So I'm going to go ahead and do that right now. If you notice, we have the alkane, we have a terminal alkyne, we don't have alkenes. So alkenes have a pKa pretty similar to alkanes. I'll go ahead and I'll show you that. So we would call these hydrogens that I'm drawing in right now vinyl hydrogens. Vinyl means directly attached to the carbon of a double bond. And so the pKa of this carbon, or this hydrogen, is about 45. So the alkane and the alkene, the vinyl proton, they have pretty similar pKa's. We will talk more about trends later, but I will point out that the terminal alkyne is 25 orders of magnitude, 20 to 25 orders of magnitude more acidic than the alkane and the alkyne, and we'll be investigating or thinking about why that is later as we continue our discussions. Now, one more pKa that's useful to know. So you can see we have water and alcohols. They're similar because the acidic proton is quite similar, right? The only difference between water and an alcohol is that the alcohol has an alkyl group in place of one of the hydrogens. So that water and alcohols are very similar in terms of acidity. But there's one alcohol that has a pretty different pKa value than just water or the generic alcohol. So this is called phenol, where the alcohol is directly bonded to the phenyl ring of this aromatic system. And phenol has a pKa of 10. So pretty useful to kind of keep this in mind if you can, that it is 1,000,000 times more acidic than water or a plain alcohol. And you can think about why that is perhaps, and we'll certainly circle back to that later. Another thing for me to point out is ammonium has a pKa of 9, and it is much different than ammonia. So amines or ammonia, they have a pKa of 35 because they're forming charged species. Here's an amide, not to be confused with the carbonyl containing functional group amide. This is amide. Yeah, it's super confusing. Amide, amide. So we can see that ammonium is much, much, much more acidic than an amine. The amine makes the negatively charged amide, and ammonium makes a neutral amine. So please keep those numbers in mind, that ammonia and ammonium are different. They have different conjugate bases, and they're going to have different pKa values. All right, so we'll think more about what's going on here and what the trends are, and thinking about explaining some of this data as we move on to the next lesson. But for now, you can memorize these pKa values for common functional groups. Before we use these pKa values to make predictions, let's take a moment and see if we can identify some of those potentially acidic functional groups on the molecules shown here. So you can pause, or you can play along. You can play along with me. So here we have a phenol, like we talked about on the previous page. Phenol has the alcohol directly bonded to the carbons of a benzene ring of a phenyl ring. The pKa of a phenolic proton is about 10, and certainly structural variations will change that a little bit, but 10 is a starting place. We have a normal alcohol, and the pKa of an alcohol is about 16. How do I know? I memorized these numbers, and you have them out next to you, and you're using them as a reference until you've memorized them. Now, all of the other protons, they are not going to be very acidic, right? All the alkane protons, all the other CHs, they're all going to have a pKa of 50, and then even the ones that are on the ring, the vinyl protons, they have a pKa of 45. So we will not consider those. pKa's of 45 and 50 are just not going to be significantly acidic. Let's look at this unnatural amino acid that we have here and identify the pKa's of these protons. So here we have a carboxylic acid. Carboxylic acids have a pKa of about 5. That's a place to start. An amine has a pKa of about 35 to 38. A terminal alkyne this has a pKa of about 24 to 25. So you want to be able to identify potentially acidic functional groups and know what their approximate pKa values are. So let's go ahead and we're going to revisit this problem that we were discussing quite a while ago, actually. So we looked at this reaction between ammonium and hydroxide. And I asked you whether or not you thought this reaction would proceed to the left or to the right. So which side of the equilibrium would be favored? And I'm guessing that you would tell me, if you could, that the forward direction would be favored and that the products would be observed at equilibrium because they're uncharged. Now I can let you know that's okay. That's a really great prediction. And in this case, you're going to be right. But you will not be right every time if you just pick species that are uncharged. So we're going to think about how to actually use that pKa data to to make a better prediction. So we can take the pKa data and we can calculate the equilibrium constant for this reaction. The equilibrium constant for this reaction will be 10 to the difference between the pKa of the product acid minus the pKa of the reactant acid. So we need to identify the acids on both sides. We have ammonium is the acid on the left, and water is the acid on the right. So the equilibrium constant here will be 1 times 10 to the pKa of the product acid is about 16. You're looking at your chart. Water has a pKa of 16. The reactant acid has a pKa of 9. It's ammonium. So this equilibrium constant is going to be on the order of about 1 times 10 to the 7. So yes, that is much, 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 much greater than 1, and thus it confirms your prediction. Well done. Let's just be absolutely sure that we remember what the value of the equilibrium constant tells you about the concentrations of reactants and products at equilibrium. The equilibrium constant is equal to the ratio of the concentrations of the products over the reactants at equilibrium. When the equilibrium constant is greater than 1, the products are favored. You have more products than reactants. When the equilibrium constant is less than 1, the reactants are favored at equilibrium. So what I like to do now is I like to practice. That's embarrassing. I like to practice predicting acid-base equilibria with pKa's. So we've already looked at ammonium plus hydroxide. But now I'd like for you to pause and take a look at acetic acid plus ammonia, and then 1-butyne plus hydroxide. And I'd like for you to do these things. Draw the Lewis structures of the reactants. And if you like, you can draw the skeletal structures, that's fine. Predict the products of the proton transfer reaction. Draw the curved arrows for the proton transfer reaction. And then determine which side of the reaction will be favored at equilibrium, plus calculate the approximate equilibrium constant using the pKa data. So once you've tried this for acetic acid plus ammonia, then come back and let's do it together. So acetic acid looks like this. I'm going to draw the skeletal structures. The really important part is that you draw out the acidic bond, and the acidic bond in acetic acid is that OH. I'll go ahead and I'll put my lone pairs in too. So now that we have these drawn out, we need to decide which is the acid and which is the base. Well, acetic acid has acid in the name, so I'm going to guess acetic acid is the acid. Ammonia is a base, and really the base just needs to have a lone pair, which ammonia does. Acetic acid is going to donate a proton, and ammonia is going to accept it. Ammonia will donate its lone pair, will use its lone pair to accept the proton from acetic acid, and the electrons in that bond will go to the oxygen that was bonded to the acidic hydrogen. And that will make acetate and ammonium. Excellent. Couple of things you might recognize. You might recognize that acetate is described by 2 resonance structures. You would be correct. You could go ahead and draw that in if you like. That will be the fact that this is described by 2 resonance structures will be significant at some point. So let's check our checklist. What else are we supposed to do here? So we drew the Lewis structures of the reactants, and we predicted the products. We drew the curved arrows, and now we need to decide which side of the equation will be favored at equilibrium. Go ahead and make your prediction, which side you think will be favored, the left or the right. And now we need to identify the acid on each side. Well, acetic acid was the acid on the left, and so acetate is its conjugate base. Ammonia was the base on the left, so its conjugate acid is ammonium. Now we need to figure out the pKa's. Acetic acid is a carboxylic acid, and so for us, if we need to estimate its pKa, we're going to estimate its pKa is about 5. Ammonium, the conjugate acid on the right side of the equation, it has a pKa of about 9. And again, I'm not just picking that out of the ether. I've memorized this chart. And so I'm looking at this chart if I haven't memorized it, or I'm gathering the information from my brain. So now if we can already tell which side is favored at equilibrium. So the side with the weaker acid will be favored at equilibrium. Think about that. The side with the weakest acid is favored at equilibrium. So which side is favored at equilibrium? Well, I hope that you said the right, because that is the correct answer. But if you didn't, that's okay. This can get a little bit confusing. So remember, larger pKa corresponds to a weaker acid. So a more positive pKa corresponds to a weaker acid. So in that case, we can tell already the right side is favored at equilibrium. Now, if we want the equilibrium constant, it's 1 times 10 to the pKa of the product acid. That would be 9 minus the pKa of the reactant acid. That would be 5, or 1 times 10 to the 4, which is, again, is much, much, much greater than 1. So products are favored at equilibrium. And again, this equation I'm getting from right here. I want you to go ahead, take all that in, and try yourself for 1-butene plus hydroxide. Let's try this together. So hydroxide here will be the base. It's the only species that has a lone pair that can accept the proton. So we start our arrow at the lone pair of hydroxide. It accepts the proton from 1-butene. And then those electrons go to carbon number 1, the carbon that was bonded to hydrogen. So now we have the conjugate base of 1-butene. And then we'll have water, the conjugate acid of hydroxide. Okay. So now we want to think about which side is favored at equilibrium. Well, we need to identify the acids on both sides of the equations and figure out what their pKa values are. So water has a pKa of 16, and the terminal alkyne has a pKa of 25. And again, I identified the functional group and I looked it up on the table until I have the table memorized. So the weaker acid is favored at equilibrium, and that'll be the left side of the equation here. This is the larger pKa, right? It's greater than 16. Therefore, this is the weaker acid. So the left side of the equation is favored at equilibrium. And if I would like to calculate the equilibrium constant, then that will be 1 times 10 to the product acid pKa minus the reactant acid pKa. So this will give me an equilibrium constant of about 1 times 10 to the negative 9, which is much less than 1 and does suggest that the reactants are favored at equilibrium. We will have more 1-butene and hydroxide than we will have the conjugate base of 1-butene and water. So this conjugate base, this is called an acetylide ion. Okay, it's called an acetylide ion. This is acetylene. Acetylide would be the anion. So the conjugate base of 1-butene is just a variation of an acetylide ion. It's substituted, right? It has an R group instead of an H. All right. This has been a long video. I know we are almost done. We're going to revisit these two molecules that we thought about a few slides ago. And we want to imagine that each of them is treated with one equivalent of a very strong base, which we're going to call B-. And we can just imagine that this base is strong enough to deprotonate the most acidic proton for each molecule. So you should predict which proton will be removed. Well, on the previous slide, when we looked at this molecule, we identified two acidic protons here in estradiol. The phenolic proton, which has a pKa of about 10, and then the normal alcohol proton that has a pKa of 16. Since the phenolic proton has a smaller pKa, it is more acidic, and the most acidic proton is going to be deprotonated by this base. So it would deprotonate here and generate the conjugate base. Magic, here's the conjugate base. Now let's try again for the unnatural amino acid. We had determined that the pKa of the terminal alkyne functional group was about 25. The pKa of the carboxylic acid would be about 5. And the pKa of the amine would be about 35. So the most acidic proton here for the unnatural amino acid will be the one with the lowest pKa, which is the carboxylic acid. So our strong base will deprotonate the carboxylic acid and generate the carboxylate as the conjugate base. So we can use that pKa data that we memorized to just think about which proton on a complex molecule will be deprotonated when it is exposed to a base. So I would like for you to spend some time with these reflection questions after the video. How can you predict whether or not an acid, HA, will be a significant acid? And how can you predict whether or not HA versus HB will be a stronger acid? So imagine you have two different acids. How can you tell which one will be stronger? And a hint, there might be similar answers to these two questions. This has been a long video, so let's go ahead and end it by making sure we have achieved the learning goals. You should be able to write proton transfer reactions for Bronsted-Lowry acid-base combinations. So some acid HA donates its proton to some base B, we'll call it B-, and that makes A- and HB. You should be able to predict which side of a proton transfer reaction will be favored for a given acid-base pair, and you want to use pKa's. So the weakest acid will be favored at equilibrium. Weakest acid will be favored at equilibrium. So for example, if HA has a pKa of 5 and HB has a pKa of 11, HB is a weaker acid, and so this side is favored at equilibrium. You should be able to calculate the equilibrium constant for a proton transfer reaction using pKa data. So again, that's 1 times 10 to the pKa of the product acid. For this example, that's 11 minus 5, the pKa of the reactant acid. So you really need to be able to identify the acids on both sides of the equation. And then finally, you should be able to provide the pKa's for common functional groups. If you see a carboxylic acid, you should identify that that is the acidic proton, and the pKa will be about 5. Or that's a good starting place anyways. 5 is a starting place. If you saw some alcohol, oh, this proton might be acidic, and a good starting place to think about its acidity is a pK of 16. So go ahead and memorize these pKa values for common functional groups that we discussed. And then you need to practice, practice, practice.